Imagine you are cruising down the highway at 70 miles per hour. You're sipping coffee, listening to your favorite podcast, feeling completely at rest. From your perspective inside the cabin, you are sitting perfectly still. Your drink isn't spilling. Your hands rest gently on the wheel. It is a brilliant illusion, a masterclass in deception, orchestrated by the everyday physics we completely take for granted. But here's the terrifying paradox. You are not still. You are a biological projectile hurtling through space at over 100 feet per second. Right now, your body possesses an immense, invisible vault of kinetic energy. You simply do not feel it because everything around you, the plush seats, the dashboard, the air itself, is traveling at the exact same speed. What happens when that peaceful illusion is violently shattered in a fraction of a second? What happens when the metal box you are sitting in suddenly meets an immovable concrete wall? Today, we are not just looking at crumpled metal. We are peeling back the invisible fabric of reality to understand the raw, unforgiving physics of a crash. You will never look at that simple strip of fabric across your chest the same way again. Let's dive in. Why? Why does a sudden stop transform us from relaxed passengers into vulnerable targets? To understand this, we need to summon the ghost of Sir Isaac Newton and his first law of motion. You probably remembered the textbook definition. An object in motion stays in motion, with the same speed and in the same direction, unless acted upon by an unbalanced force. But let us translate that from textbook speak into the terrifying reality of the highway. This principle is called inertia, and it is the invisible phantom riding shotgun with you on every single journey. Imagine our car hitting that solid concrete wall at 70 miles per hour. The front of the vehicle crushes, absorbing energy, and the car comes to a complete, violent halt in about 1/10 of a second. But here's the crucial, chilling fact. The car stopped, but you did not. You are not physically fused to the car just by resting on the leather seat. Your body, guided by the relentless law of inertia, is perfectly happy continuing its forward journey at exactly 70 miles per hour. This leads us to a grim realization that trauma surgeons and crash investigators know all too well. A severe car crash is never just one single collision. It is actually a sequence of 3 distinct, terrifying impacts. The first collision is the obvious one. It is the metal of the car striking the concrete wall. The kinetic energy bends the steel frame, shatters the tempered glass, and crumples the hood. But because of inertia, your body is still hurtling through the cabin. This triggers the second collision, the human impact. If you are unrestrained, you become a human projectile, flying forward at the original speed of the vehicle. You will strike whatever happens to be directly in your path, the steering wheel, the hard plastic dashboard, or the impenetrable windshield. At this point, you become the unbalanced force hitting a suddenly stationary object. Then comes the third collision, the unseen one, and tragically, often the most deadly, the internal impact. Just as your body was moving inside the cabin of the car, your internal organs, your brain, your lungs, your liver, are moving freely inside the cavity of your body. When your ribcage forcefully hits the steering wheel and abruptly stops, your internal organs keep moving forward until they crash into your skeletal structure. Your brain violently slams against the inside of your skull. Your heart pulls dangerously against its vital arteries. So, how do we possibly survive this cascading sequence of physics? We have to cleverly manipulate the fundamental equation of force. Force is equal to mass multiplied by acceleration, or in this specific case, deceleration. Your mass is your body weight. The change in speed is going from 70 down to 0. Neither of those numbers can change once the crash sequence begins. The only variable we can potentially control, our golden ticket to survival, is time. Momentum is a demanding master. It requires that all that kinetic energy be transferred somewhere. If you hit a rigid steering wheel, Your deceleration time is a tiny fraction of a millisecond, which means the resulting force exerted on your bones and organs is astronomical. It is an unsurvivable spike of energy. But what if we could stretch that violent split second out? That is the sheer genius of the seatbelt. It is not merely a restraint. It is a mechanism to tether your mass to the vehicle, forcing you to slow down together with the car, rather than after it. It ensures you partake in the car's prolonged deceleration, turning a lethal, instantaneous stop into a survivable physics transaction. To truly appreciate the terrifying majesty of these forces, we must step outside the mundane setting of a highway and push up perspective to the absolute extremes. Let us embark on a thought experiment that stretches the concepts of inertia and momentum beyond our everyday experience, removing all earthly variables to expose the raw, underlying physics. Imagine for a moment that you are sitting in a vehicle, floating in the deep, silent vacuum of interstellar space. There is no gravity pulling you rigidly down into the driver's seat. There is no atmosphere creating air resistance against the windshield. You are completely untethered from the usual forces of Earth. Now, imagine your spacecraft car is traveling at a constant speed of 100 miles per hour relative to a massive, perfectly stationary asteroid directly in your path. Because there is no friction or gravity, you do not even need to press an accelerator to maintain the speed. You are simply drifting, completely at peace, embodying Newton's first law of motion in its absolute, purest form. Suddenly, the front bumper of your vehicle strikes the asteroid. The metal crumples, and the vehicle comes to an instantaneous, dead halt. What happens to you? On Earth, gravity and the friction of your clothing against the seat might offer a microscopic, almost negligible amount of resistance. But here in the void of space, your isolation with inertia is absolute. When the car stops, you absolutely do not. You will continue to float forward at precisely 100 miles per hour. Without a restraint system tethering your mass to the vehicle, you will travel at that exact speed until you violently collide with the interior dashboard. In the vacuum of space, this illustrates how utterly independent your body's momentum is from the mechanical shell surrounding it. Now, let us bring our thought experiment back down to Earth, but scale up the variables to understand the monstrous nature of the mathematics involved. We need to talk about kinetic energy, which is the actual physical currency of any crash. The equation for kinetic energy is 1/2 times mass times velocity squared. I want you to focus heavily on that final word, squared. It is the silent, mathematical killer present in every high-speed collision. Most people intuitively believe that if you double your driving speed, a resulting crash will be roughly twice as bad. The physics tell a vastly different, far more lethal story. If you are traveling at 30 miles per hour and then accelerate to 60 miles per hour, you have doubled your speed. But because the velocity is squared in our equation, you've not doubled your kinetic energy, you have quadrupled it. If you increase your speed from 20 miles per hour to 80 miles per hour, a fourfold increase in speed, your body is now carrying a staggering 16 times more destructive energy. This exponential curve is exactly why high-speed crashes are so disproportionately devastating. In a fraction of a second, the vehicle and your fragile body must suddenly dissipate an astronomical amount of energy. The structural integrity of engineered steel and the biological limits of human bone are strictly finite. When you push the velocity higher, you quickly surpass the threshold of what physical materials can possibly absorb without failing. The speed limits posted on our highways are not arbitrary numbers chosen by local bureaucrats. They are strict mathematical boundaries, calculated specifically around the human body's biological tolerance for kinetic energy transfer. By looking at a crash through the lens of zero gravity and exponential mathematics, the comfortable illusion of safety inside a speeding metal box vanishes. A collision is not a random accident. It is an unforgiving, instantaneous accounting of cosmic energy. And in that violent mathematical transaction, Your only defense is understanding the physics at play. Let us bring this back from the cold vacuum of space to the driveway of your own home. The terrifying physics we just explored are exactly what automotive engineers battle every single day. Modern cars are not just vehicles. They are highly sophisticated physics management systems designed from the ground up to manipulate time, force, and momentum in a desperate bid to keep you alive. The most prominent example of this manipulation is the crumple zone. If you look at a vintage car from the 1950s, you see a rigid, unyielding block of heavy steel. People used to think the stiffness meant safety, assuming a strong car protected its occupants. Physics tells us the exact opposite. When a perfectly rigid car hits a wall, the deceleration time is practically zero. Because it does not bend, it transfers all of that immense, deadly kinetic energy directly into the passenger cabin, and consequently, right into the fragile bodies of the people inside. Modern engineers flip this logic completely upside down. They design the front and rear of your car to intentionally destroy themselves. Crumple zones act like giant metallic accordions. By deliberately folding, buckling, and crushing upon impact, they essentially steal the kinetic energy from the crash and use it to bend the steel frame. More importantly, this highly choreographed crushing process buys you time, perhaps an extra tenth or 2/10 of a second. As we learned from our momentum equation earlier, increasing the deceleration time drastically lowers the peak force exerted on your body. The front of the car violently sacrifices itself so that the passenger cabin remains an untouched island of safety. Then we have the supplemental restraint system, better known as the airbag, which is truly a masterclass in controlled chemical explosions. An airbag does not trigger based on the physical impact of the bumper. It triggers based purely on the physics of deceleration. Microscopic accelerometers built into the car's computer continuously monitor your speed. When they detect an unnatural, violent drop in velocity, they ignite a solid chemical propellant. This reaction creates a massive, instantaneous burst of nitrogen gas, inflating the nylon bag in about 30 milliseconds, literally faster than the human eye can blink. It provides a soft, forgiving cushion that catches your forward-moving mass. It further extends the time your head and chest take to come to a complete stop, effectively neutralizing that catastrophic secondary collision with the dashboard. But the true future of physics and automotive safety is shifting from damage mitigation to pure, algorithmic prediction. We are entering the era of the active physics engine. Tomorrow's autonomous vehicles are equipped with an array of LiDAR, radar, and artificial intelligence that constantly calculate the vectors, velocities, and potential kinetic energies of every single object around them in real time. If a collision becomes mathematically unavoidable, the car's computer can proactively prepare for the transfer of energy. It can dynamically adjust the suspension to lower the center of gravity, pre-tension the seatbelts to lock you in perfect position before the impact even occurs, and calculate the precise microsecond to deploy individual airbags for maximum energy absorption. We are moving from simply surviving the laws of motion to actively outsmarting them. The vehicle of the future will not merely be a protective cage of steel. It will be an invisible, predictive mathematical shield, constantly solving complex physics equations thousands of times a second to keep the unforgiving ghost of inertia permanently at bay. So, the next time you hear that reassuring click of the seatbelt across your chest, remember what you are actually doing. You are not just following the law or blindly trusting a piece of woven nylon. You are actively engaging with the fundamental laws of the universe. You are striking a vital mathematical bargain with Sir Isaac Newton himself, buying the precious milliseconds your body needs to survive the violent, unforgiving forces of a sudden stop. Physics is not just equations on a chalkboard. It is the ultimate co-pilot, riding with you every single day. If this journey through the unseen forces of our daily lives changed the way you see the world, hit that subscribe button and join our expedition team. We decode the universe, one hidden truth at a time. And speaking of unseen forces, what exactly is keeping you pinned to your seat when a roller coaster loops completely upside down? We will be breaking down the terrifying thrill of centripetal force in our next video. You will not want to miss it. Stay curious, stay safe, and I will see you in the next one.